Dear students, welcome to the EPG Pathshala. I am Dr. Rajkishore Sharma from Chemistry Department of Delhi University. Today, we are going to discuss about the module X-ray Photoelectron Spectroscopy and Introduction. This is under the paper of Surface Analytical Techniques 2. So, outlines of the topics that we are going to cover today: the photoelectric effect, and how do electrons eject from metals, then relationship between A, C, D and J, equations of photoelectric effect, stopping potential, then we will discuss what is XPS, what is Fermi level will also be discussed, and spectroscopic notations. We will discuss energy scale, inelastic scattering, sample spectrometer diagram, X-ray source and a depth analysis, and at the end we will discuss the advantages and disadvantages of XPS. Let us now discuss the history of X-ray photoelectron spectroscopy. Firstly, Henry Hertz observed the emission of electrons in 1887 when he got electric spark after illuminating electrodes in ultraviolet light. After 18 years, in 1905, Einstein explained the photoelectric effect and proposed that a beam of light is not a wave which propagates through space. Rather, it is a collection of discrete wave packets called photons. Einstein got the Nobel Prize in 1921 for his discovery of the law of photoelectric effect. Rutherford and his co-workers in 1914 recognized that kinetic energy of electron, that is, the difference between X-ray energy and the electron binding energy. Robinson and Young observed the line shift caused by chemical bonding in 1930. That is, they observed the effect of different types of bonds present in a compound, or we can say that how an element is attached with different type of bonds. A main step was taken by Professor Kai Shengman and his research group in Uppsala University in Sweden to build up an electron spectroscopy as a tool in the determination of electronic structure. The first high-resolution spectrum employing X-ray photoelectron spectroscopy of sodium chloride was recorded by Professor Kai in 1954. They revealed that potential of XPS, the first commercialized XPS machine came into the market in 1970 after their findings. This technique became apparent, which could distinguish between metal and its oxides, as well as it was able to explain chemical state information for non-metallic elements as well. Due to all these chemical effects, the Swedish group gave the term electron spectroscopy for chemical analysis, or this is, in short, this is abbreviated as ESCA. For the development of XPS technique, Professor Kai in 1981 was awarded the Nobel Prize in Physics for his discovery. Before going into depth of XPS technique, we need to know about the surface. So now we will start with surface. What happens at surfaces is extremely important in a vast range of applications, from environmental corrosion to medical implants. A surface can be thought of as the interface between the different phases, that is solid, liquid or gas. We can think of the surface as the top layer of the atoms, but in reality the state of this layer is very much influenced by the 2 to 10 atomic layers below it. This is about 0.5 to 3 nanometer. Surface modification treatments are often in the range of 10 to 100 nanometer thickness. Less than 100 nanometer can be thought of as the bulk. Higher than 100 nanometer can be thought as of the bulk. Surface analysis encompasses techniques which probe the properties in all these ranges. Now about the photoelectric effect. The photoelectric effect is a phenomena in physics. In this phenomena, electromagnetic radiation is used to irradiate the metal surface. Electromagnetic radiation of series of particles, and these particles are called photons. So when a photon hits an electron on a metal surface, the electron can be emitted, and the emitted electrons are called photoelectrons. The photoelectric effect is also studied in the field of chemistry, such as quantum chemistry and electrochemistry. Photon energy is the energy carried by a single photon. The amount of energy is directly related to the photon's electromagnetic wavelength and frequency. The higher the photon's energy, higher the photon's frequency, the higher is the energy. Equivalently, the longer the photon's wavelength, the lower is its energy. Photon energy is solely a function of the photon's wavelength. Other factors, such as the intensity of the radiation, do not affect photon's energy. In other words, two photons of light with the same color and therefore same wavelength will have the same photon energy, even if one was emitted from a wax candle and the other from the sun. Photon energy can be represented by any unit of energy. Among the units commonly used to denote photons energy are the electron volt, or we write EV, and the joule. The electromagnetic spectrum includes, in order of increasing frequency and decreasing wavelength, radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays, and so on. The energy of an individual photon is quantized and is greater for photons of higher frequency. The electromagnetic spectrum extends from below the low frequency used for modern radio communication to gamma radiation at the short wavelength and high frequency, thereby covering wavelengths from thousands of kilometers down to a fraction of the size of an atom. Visible light lies towards the shorter end with wavelength from 400 to 700 nanometers. The limit for long wavelength is the size of the universe itself, while it is thought that the short wavelength limit is in the vicinity of the Planck's length. Until the middle of the 20th century, it was believed by most physicists that this spectrum was infinite and continuous. The distinction between X-rays and gamma rays is partly based on sources. The photons generated from nuclear decay or other nuclear and subnuclear particle processes are always termed gamma rays, whereas X-rays are generated by electronic transitions involving highly energetic inner atomic electrons. In general, nuclear transitions are much more energetic than electronic transitions. So, gamma rays are more energetic than X-rays. Now, what are the rules? There are certain rules which should be obeyed by the photon during interaction with other particles. Like, each photon only interacts with one electron. It delivers its energy to the electron and disappears. Because it is a packet of pure energy and nothing else, so it disappears after transferring the energy. Electron now has extra energy. If it has enough extra energy, it can leave the metal atom. So, only photons above the threshold frequency, we call F0, will cause photoelectric emission. How come more intense or brighter radiation doesn't cause emission? There's a good question here. How come more intense or brighter radiation doesn't cause emission. More intense radiation simply means that more packets of energy, that is, more photons, are delivered each second. So the rate of delivery of photons is high. But the energy of each packet is unchanged. So if there wasn't enough energy to cause photoelectric emission, making it brighter won't change anything. But the question arises that how do electrons eject from metal surface? Electrons present in the metal have minimum amount of frequency. That frequency is called threshold frequency. It is represented by V0, nu naught. So to eject electrons from the metal surface, the frequency of incident light must be high as compared to the threshold frequency of the electron present in the metal. If energy or frequency of the incident light is less than the energy of the electrons present in the metal, then electrons cannot be ejected from the surface of metal. Thus, we can say that the energy of incident light must be high to eject electrons. Photoelectrons are ejected electrons from metal surface have some energy. That energy is called the kinetic energy. Based on the wave model of light, it is observed that by increasing the frequency of incident light, the kinetic energy of photoelectrons can be increased, and by increasing the light amplitude, current can be increased. On the above assumption, Einstein explained that light just behaved like a stream of photons having energy E is equal to h nu, where h is the Planck's constant and nu is the frequency of light. Now, the other term work function is introduced, and we need to understand work function, which is the minimum amount of energy required to eject a delocalized electron from the surface of the metal. It is represented by the symbol phi. Now about the setup. Here we will see a very famous experiment that led to Einstein's Nobel Prize. It has to do with how electrons and photons interact. The basic idea of this experiment is as follows. By sending light on a metal target, we see that electrons are ejected. These electrons can create detectable current. By applying a counter voltage, we can change the current and determine number of electrons ejected and their individual energy. By shining different frequency light with various intensities, we can study in details the interaction between light and electrons. Here an adjustable voltage is also applied, and voltage can be forward or reverse biased, which slows down the electrons. Photoelectrons returns to cathode through an emitter that records the current. Now, some experimental results. Here we will see some results. If photoelectrons get ejected when you shine monochromatic light on the target, the current increases. When you increase the intensity or brighter light, it means more photoelectrons. But above a cutoff wavelength, no photoelectrons get ejected, no matter how great the intensity of the incident radiation is. And for the wavelengths below the cutoff, decreasing the radiation to very low intensities doesn't completely eliminate the production of photoelectrons. From the graph, we can see the relation between kinetic energy of photoelectrons, light amplitude, and electron current. Symbol A represents the ampere, which is the unit of electric current. J represents the joule, which is the unit of kinetic energy, and CD represents the candela, which is the unit of the light amplitude or luminous intensity. In general, more photons emitted per unit time, the greater the intensity of light. A single photon have wavelength and speed. Therefore, the energy of a single photon is not measured by its amplitude. However, the amplitude of a light wave depends on the number of photons per second being emitted. From the first graph, it can be seen that light amplitude and electron current are linearly dependent when frequency of incident light is greater than threshold frequency. In the second graph, it can conclude that electron kinetic energy is independent of light amplitude. Now, equation of photoelectric effect. The equation of photoelectric effect can be written as Ke is equal to, Ke refers to the kinetic energy, Ke is equal to h nu minus phi, where phi is the work function, is equal to h nu naught. Then photoelectric effect equation becomes Ke is equal to h nu minus h nu naught, and kinetic energy can be positive only when nu is greater than nu naught. That is the necessary condition for the photoelectric effect to occur. If the incident frequency is equal or less than threshold frequency, then kinetic energy becomes equal to 0 or negative. That means the electrons cannot be ejected from the metal surface. Thus, we can say that kinetic energy depends upon the frequency of incident light. In general, higher frequency photons have more energy, so they should make the electrons come flying out faster. Thus, switching to light with the same intensity but a higher frequency should increase the maximum kinetic energy of the emitted electrons. If you leave the frequency the same but crank up the intensity, more electrons should come out because there are more photons to hit them, but they will not come out any faster because each individual photon has the same energy. And if the frequency is low enough, then none of the photons will have enough energy to knock an electron out of an atom. So, if you use really low frequency light, you shouldn't get any electrons, no matter how high the intensity is. Whereas, if you use a high frequency, you should still knock out some electrons even if intensity is very low. Now, the stopping potential. Maximum kinetic energy can also be calculated using stopping potential. Stopping potential is the potential necessary to stop the electron from one side to other side, that is from cathode to anode, or we can say that the voltage required to completely balance the kinetic energy of electrons ejected from a material surface. The maximum kinetic energy of the photoelectron can be calculated as Ke is equal to EV naught, where Ke is equal to the product of EV naught, where V naught is the stopping potential and E is the charge of the electron. Now, how do we interpret this? Slope is always found sum for all targets. Y-intercept is different from different target materials. Photoelectric effect equation becomes EV naught is equal to H into nu minus nu naught. V naught is the stopping potential, H nu is the work function of the metal. Work function is the minimum amount of energy required to remove an electron, and H is equal to 6.63 into 10 raised to the power minus 34, that is the Planck's constant. X-ray photoelectron spectroscopy or XPS is the surface analytical technique which is used to investigate the chemical composition of sample surfaces. It provides wide information about the chemical structure of the catalyst composition. Even you can find dispersion also, because you can just just like in terms of the bond or energy which is required, the kinetic energy of the electron. It measures that and related to the binding energy of the electrons, which are the core electrons. XPS is also known as electron spectroscopy or chemical analysis of or ESCA, an abbreviation introduced by Kai Shengban research group to emphasize the chemical information that the technique provides. Now, what is the Fermi level? X-ray photoelectron spectroscopy works on the principle of photoelectric effect. In XPS, X-ray photons are irradiated with a sample that leads to injection of photoelectrons as shown in figure. X-ray photons interact with an electron in K shell, causing the emission of 1s photoelectron. The resulting K shell vacancy is filled by an electron from a higher level, which can lead to either X-ray fluorescence or the radiation less de-excitation process of OJ emission. The determination of kinetic energy of the ejecting electron is the groundwork of experimental XPS. Kinetic energy, binding energy, and work function can be explained by photoelectric effect, which we have discussed already. From the diagram above, work function can be defined as the energy difference between Fermi level and the vacuum level. The kinetic energy of electron is not an intrinsic material property, but it depends on the photon energy of the X-rays employed. Kinetic energy is experimental quantity measured by the spectrometer. Fermi level can be defined as the highest energy state that occupied by electrons in a material at absolute zero temperature. So if we increase the temperature, electrons can jump in higher energy states. From the last figure, it can be seen that binding energy or BE is the energy that can be defined of a whole state as the energy difference between initial and the final state of the species containing core hole. BE is an intrinsic material property of the photoelectron and does not depend on X-ray photon source. Binding energy of elements show slight variation and depends upon the exact environment of atom, ions or molecules. Now, the spectroscopic notations. Spectroscopic notations is used in XPS. If it is used to describe which electrons are involved with each of the observed transition. In general, the spectroscopic notation can be represented as where n is the principal quantum number, L is the orbital angular momentum, J is the total angular momentum. The total angular momentum is found equal to L as. Thus, if n is equal to 1, L is equal to 0 and spin quantum number S is equal to plus minus half, and then J will be half, and it can be represented as 1s 1 by 2, 1s half, and if n is equal to 2, L is equal to 1, S is equal to plus minus half, then J will be 3 by 2 and 1 by 2, and it can be represented as 2p 3 by 2 and 2p 1 by 2. Now about XPS energy scale. The OJ electrons are emitted when kinetic energies that are only dependent on the electronic state of the element responsible for the ejected electron. Photoelectron line energies depends on the photon energy. OJ electron line energies not depend on the photon energy. Now, binding energy scale is considered since photoelectron peak come on same binding energy with different primary source. Photoelectron line energies do not depend on the photon energy. OJ electron line energies depends on the photon energy. About the emission of electrons. Trajectories of emitted electrons from the sample surface. It is number 1, if it were captured before reaching to the surface and never reached to the surface. Follows root 3. Number 2, if electrons reaches the detector without any energy loss, these electrons contribute to XPS peak follows root 1. Number 3, if it lost energy before reaching the surface, that is, if it escaped from the solid and reached the detector, but with E less than E0. These electrons contribute to background of the XPS spectrum, called inelastic scattering, which follows route 2. Each inelastic scattering event leads to number 1, a reduction in the electron energy, and number 2, a change in the direction of travel. Now about inelastic scattering. So from the figure, it can be seen that electrons emitted from solid surface shows low energy peak in spectrum, that is called inelastic scattering, and these electrons contribute to the background of the XPS spectrum. And also it can be seen that electrons without energy loss show characteristic peaks in XPS called photoemission peak. In figure, there is the energy level diagram for a conducting sample. This diagram is called sample spectrometer energy level diagram for conducting sample. You can see that Fermi levels of sample and spectrometer are aligned, and we only need to know the spectrometer work function. For conducting specimens, a fine strip of conducting paint, in addition to the adhesive tape, is all that is necessary to prevent sample charging. Solvent in the conducting paint can cause the pump down time to extend as they evaporate in the vacuum. Alternatively, metal tape with a metal loaded, that is conducting adhesive, may be used. In the case of powders, the best method is embedding them in indium foil. But if this is not feasible, dusting them into double-sided adhesive tape can be very satisfactory alternative. This is a sample spectrometer energy level diagram for non-conducting sample. In an insulating sample, the emitted electrons cause a positive potential, which subtract from the kinetic energy and is increasing until electrons from the surrounding limit of the potential of the sample. For insulators, the conduction band is empty, and such a connection does not exist. Therefore, any charge accumulation will shift the Fermi potential to higher values for negative and to lower values for positive charges. There are no free electrons or holes in the insulator. Its Fermi level, or virtual actually, its Fermi level cannot be equilibrated with the Fermi level of the detector. So, ECH can be determined by electrically calibrating the instrument to a spectral feature. In XPS, high intensity X-ray beam with a narrow line width gives best spectroscopic result. Most commonly used X-ray sources are aluminum K-alpha, magnesium K-alpha. Both have line width less than 1 electron volt. Other than this, X-rays can penetrate the sample to depth on the order of a micrometer. X-rays cover area about 1 into 1 square centimeter. But electrons are extracted only from narrow solid angle, that is 1 into 1 millimeter square. Useful electron signal is obtained only from a depth of around 1 to 10 nanometer of the surface. XPS has many advantages. It can identify the elements present in a sample as well as provide information about chemical bonding. It means if an element is present in a compound has different bonding, then such type of information can be provided by XPS. Other than this, if an element has bonding in different compound, then in each case XPS will give same binding energy of the element. Thus, it can give huge information about different types of chemical bonds in a material. XPS also uses the non-destructive depth profiling, that is called angle resolved XPS or AR XPS. In AR XPS, without etching the specimen, depth information can be obtained. Along with qualitative analysis, quantification of chemical composition is also possible. That is, we can calculate amount of particular element present in a specimen. XPS can also be used to image the surface of a sample. XPS elemental mapping give spatial distribution of elements on a surface. Surface sensitivity of XPS is also found very high, about 10 to 100 nanometer. Thin film thickness of native oxides such as SiO2, Al2O3, etc. can also be calculated using XPS. XPS technique also has many disadvantages, like requirement of high vacuum is necessary. Hydrogen and helium are essentially impossible to detect by X-ray photoelectron spectroscopy. Helium is not normally present as a solid, and even when present in case of implanted in a solid, its 1s orbital has a very small cross section for photoemission. Hydrogen also has an extremely small photoelectron cross section and suffers from having to share it only electron in forming compounds, which then resides in a valence like orbital. It is very expensive technique. It requires large area for samples. XPS takes much time for sample analysis, generally 30 minutes to 8 hours per sample. Now we would conclude the introduction part of XPS. For ejecting electrons from metals, energy of incident light should be higher than energy of electrons present in the metal. Kinetic energy of photoelectrons can be calculated using photoelectric effect equation. Ke is equal to h within bracket nu minus nu naught. Electrons go to the detector without any energy loss, shows characteristic peak called photoelectron peak. Electrons go to the detector with some energy loss, show XPS background called inelastic peak. Binding energy scale is considered. Both conducting and non-conducting samples can be analyzed. So XPS is a surface analytical technique which is used to investigate the chemical composition of sample surface basically. It has been observed that high intensity X-ray beams with a narrow line width gives best spectroscopic result. So always consider high intensity beam. Other than this, we talk about advantages and disadvantages of XPS. Thank you.